Hello students, in previous class we already discussed about the conservation principle for mechanical energy. That means in an conservative force field, the total mechanical energy of a system is conserved. That means the total initial kinetic energy and potential energy of the system is exactly equal to the total final kinetic energy and final potential energy of the system. And we also verified this for a freely falling body when the air resistance is neglected, and same for a body projected upward vertically and for a simple pendulum also. So today we are going to discuss about another concept that is known as collision. So what is collision? The term collision is defined as it is the process when two bodies interact with each other. Okay, the process of interaction of two bodies or two particles is known as collision, or in simply we can say that when two bodies or two particles collide with each other, that process is known as what? Collision. So collision can be defined as it is the process of interaction of two bodies or particles. Okay, so the process of interaction of two bodies or particles is known as what? Collision. Clear? So in nature, the collision can be of different types depending upon the conservation of the kinetic energy of the particles, and also it depends on the direction of motion of the particles before and after collision. Clear? So depending upon the conservation of kinetic energy of interacting particles or body, and the direction of motion of the interacting particles depending upon the conservation of kinetic energy of the interacting particles and the direction of motion of the interacting particles. Collision can be of different types. Okay, so two things are to be considered. One is the kinetic energy of the interacting particles, or the conservation of the kinetic energy of interacting particles, and also the direction of motion of the interacting particles. The collision can be of different types. Clear? So now let us discuss the different types of collisions. So types of collision. So based upon the conservation of kinetic energy, of kinetic energy of the interacting particles, collision are of three types. Okay, according to the conservation of kinetic energy of the interacting particles, collision are of three types. First one is perfectly elastic. So what is the meaning of perfectly elastic? In this type of collision, the momentum and kinetic energy of the interacting particles is conserved. Okay, so if in the type of collision the momentum and the kinetic energy of the interacting particle is conserved, then that type of collision is known as what? Perfectly elastic collision. So here we can write the momentum of the system before collision is equal to the momentum of the system after collision, and also the kinetic energy of the system before collision is equal to kinetic energy of the system after collision. Clear? So for perfectly elastic collision, you have to remember the momentum of the system. Here I am considering the total momentum, linear momentum of the system, not a single particle. The momentum of the complete system before collision is equal to the momentum of the complete system after collision, and same as that for the kinetic energy. The kinetic energy of the complete system before collision is must be equal to the kinetic energy of the system after collision, and these are the condition for what type of collision? Perfectly elastic collision. Clear? And here also we can write the total energy of the system is also conserved. Okay, so you have to remember the conditions for what? Perfectly elastic collision. Then the second type of collision, that is perfectly inelastic collision. Okay, so what is perfectly inelastic collision? In this type of collision, momentum of the system or interacting particle particles is conserved, but kinetic energy of the interacting particles is not conserved. Okay, the momentum of the interacting particles is conserved, but the kinetic energy is not conserved. Clear? Then this type of collision is known as perfectly inelastic collision. So what are the conditions for perfectly inelastic collision? So for perfectly inelastic collision, the condition for this: momentum of the system before collision is equal to momentum of the system after collision, because as momentum is conserved, but kinetic energy of the system before collision is very much large in comparison to the kinetic energy of the system after collision. Clear? But here also the total energy of the system before collision is equal to total energy of the system after collision. The total energy is conserved. But so for perfectly inelastic collision, the momentum is conserved, the total energy of the system is conserved, but the kinetic energy of the complete system before collision is very large in comparison to the kinetic energy of the system after collision. So these are the conditions for perfectly inelastic collision. You have to remember the conditions. Okay. So next, the third type of collision, that is semi-elastic or semi-inelastic collision. So third type of collision, that is you can say elastic, or you can say semi-inelastic. Okay. So in this type of collision, again the momentum is term of the interacting particles is conserved, but the kinetic energy is not conserved. Okay. So in this type of collision also the momentum is conserved, but kinetic energy is not conserved. But what are the conditions? So as I am writing here, that the momentum of the system before collision is equal to momentum of the system after collision, because momentum is conserved, but the kinetic energy of the system before collision is less than that of kinetic energy of the system after collision. Okay, but here also the total energy of the system before collision is equal to total energy of the system after collision. So these are the conditions for what? Semi-elastic collision. So you have to remember that in case of semi-elastic collision, the kinetic energy before collision is less than that of kinetic energy after collision. But in case of perfectly inelastic collision, it is highly less in comparison to after collision. Clear? So these are the conditions depending which we can distinguish between elastic, perfectly inelastic and semi-elastic or semi-inelastic collision. Okay. So these are the three types of collision depending upon the conservation of kinetic energy. Next, based upon the direction of motion, based upon the direction of motion of the interacting particles, based upon the direction of motion of the interacting particles, collision are of two types. Okay, one dimensional collision, or it can say a head-on collision. So what is one dimensional collision or head-on collision? The direction of motion of interacting particles before collision is equal to the direction of motion of the interacting particles after collision. Okay. So if the direction of the interacting particles motion is same as that of direction of the motion of the interacting particles before and after collision, then that is one dimensional collision. That means if there is two bodies A and B, They are moving with different velocity v1 and v2 in this direction. And if these two bodies collide and after collision, they are moving along the same direction, then this type of collision is known as what? One dimensional or head-on collision. Clear? The next type is two dimensional or oblique collision. So what is two dimensional or oblique collision? So in this case, if the direction of motion before collision is not equal to the direction motion after collision. Clear? That means if here is a body which is moving along this direction and here is another body which is moving along same direction with v2 velocity and before collision, and after collision the body 1 is move along this direction with v1 dash velocity and the body 2 will move along this direction with v2 velocity. Then this type of collision, as before collision they are having motion along same direction, but after collision the motion will be in different direction. Then in this case the collision is said to be what? This is the condition for after collision. The collision is oblique or two-dimensional collision. Clear? So these are the type of collisions depending upon the direction of motion of the interacting particles before and after collision. Clear? So next we are going to discuss about coefficient of restitution. Is an important term, you have to remember it. Coefficient of restitution denoted by small e. So what is coefficient of restitution? So it is defined as E is equal to, E can be written as the velocity of separation or you can say the relative velocity of separation magnitude of relative velocity of separation divided by the magnitude of relative velocity of approach. Okay, this is defined as the E or coefficient of restitution, or it can also be defined as the impulse of reformation divided by impulse of deformation. Okay, so you can define the coefficient of restitution as the relative velocity of separation, magnitude of relative velocity of separation with respect to the magnitude of relative velocity of approach, or you can derive it as the impulse of reformation with respect to impulse of deformation. Clear? So what is relative velocity of separation and relative velocity of approach? So to understand this, let consider here is a body of mass m1 and here is another body of mass m2. Clear? Let the mass m2 is moving along this direction with velocity u2 and this body is moving along this direction with velocity u1. These are the condition of before collision. Clear? And when they collide and provided here u1 is greater than u2, so as the velocity of m1 is greater than velocity of m2. That's why there will be a chance the both will collide with each other. So during collision, what will happen? So when both the blocks or bodies will collide with each other, so this is during collision, a force act on this block along this direction, the normal force, which is impulsive in nature, because this is very short period of time they will collide or they will be in interact with each other, and their same force will act along this direction, and due to this impulsive normal force they will get separated. So after collision, what will happen? The block 1 or m1 moves along this direction with certain final velocity v1, and similarly the block m2 will move along this direction to certain velocity v2, and in this case v2 is greater than v1, as due to the impulsive force the velocity of the block m2 will increase, and due to this impulsive force the velocity of block m1 will decrease. So in this particular case, what is E? According to the definition, we know E is defined as what? The relative velocity of separation divided by relative velocity of approach. So what is relative velocity of separation? These are the velocity with which the two bodies will get separated, and as here v2 is greater than v1, so what is the relative velocity of separation? The relative velocity of separation will be v2 minus v1, and we are taking the mod divided by the relative velocity of approach, as these are the velocities with which the two bodies will approach each other. So what is relative velocity of approach? As here u1 is greater than u2, so relative velocity of approach will be u1 minus u2. So this is defined as what? The coefficient of restitution. It has no unit and dimension. Okay, so coefficient of restitution has no unit and dimension because it is a perfect ratio, velocity with respect to velocity. Clear? So this is defined as what? Coefficient of restitution, which can be defined by the relative velocity of separation divided by relative velocity of approach. Clear? So for perfectly elastic, you have to remember the values. For perfectly elastic, collision, the value of E is equal to 1. Okay, for perfectly elastic collision, the coefficient of restitution is equal to 1. So if coefficient of restitution is equal to 1, so we can write what? V2 minus V1 divided by U1 minus U2 equal to 1. That means the relative velocity of approach must be equal to relative velocity of separation. Clear? Similarly, for perfectly inelastic, E equal to 0. Okay, for perfectly inelastic, E equal to 0. That means for perfectly inelastic, the velocity of separation becomes 0. Okay, so perfectly inelastic I am writing here. So for perfectly elastic collision, E equal to 1. So this implies the relative velocity of separation is equal to the relative velocity of approach. But for perfectly inelastic, E equal to 0. This implies the relative velocity of separation is 0, or both the velocities during separation for both the bodies will be same. And in general case, for semi-elastic, E lies between 0 to 1. Okay, this is the practical condition, because in our nature no collision is perfectly elastic or no collision is perfectly inelastic. Most of the collisions in practical case is semi-elastic. That's why the coefficient of restitution lies between 1 and 0. But what are the case when the collision will be perfectly elastic. In this type of case, when the collision will be perfectly elastic, that means the velocity of the particles before collision and after collision will remain nearly equal. Clear? So, in perfectly elastic collision, when a body collide with another body, the collision will be perfectly elastic, and the perfectly elastic collision generally considered to be the collision between subatomic state. That means electron-electron collision or proton-proton collision or electron-proton collision. When collision takes place in atomic or subatomic levels, then those type of collisions are generally considered as to be perfectly elastic collision. Clear? And what is perfectly inelastic collision? When after collision the velocity of both the particles remain same or they stick to each other, but not always. Perfectly inelastic collision means after collision the particles will stick to each other. The general statement is what? For perfectly inelastic collision, the velocity of separation will become same. That means maybe the velocity of separation equal to each other, or the velocity of separation along the line of impact become same. Clear? So for perfectly inelastic collision, the velocity of separation becomes equal with each other. May they get separated from each other with same velocity, or may they move with as a single object with same common velocity. Clear? And in general, semi-elastic collision, the day-to-day life, the collisions which we are observing are generally what? Semi-elastic collision. Neither they are perfectly elastic nor they are perfectly inelastic. Clear? So this is all about coefficient of restitution. You have to remember all these values. For perfectly elastic, the coefficient of restitution is 1. That means the velocity or relative velocity of separation is equal to relative velocity of approach. And for perfectly inelastic, as the velocity of separation of both the object is equal, so the coefficient of restitution will be 0. And for semi-elastic, the coefficient of restitution lies between 0 and 1. Clear? And coefficient of restitution has 0 unit and no dimension, because it is a perfect ratio of two relative velocities. Clear? So next we are going to discuss about one-dimensional perfectly elastic collision or one-dimensional or head-on perfectly elastic collision. So next we are going to discuss about one-dimensional perfectly elastic collision. Okay, so one-dimensional perfectly elastic collision. So just consider two bodies. M1, which is moving along this direction with velocity u1, and another body of mass m2, which is move along this direction with velocity u2. These are the condition. Here u1 is greater than u2. That's why they can collide with each other. This is the condition of before collision. Okay. During collision, they will interact with each other for a very small period of time. Due to which, this is the condition for during collision. This is M1, this is M2. And they interact for a very short period of time, for which two impulsive normal reaction force act on each other, due to which their velocity get changes. And due to this interacting force or impulsive force, the two bodies will get separated. And as this is a one-dimensional perfectly elastic collision, the complete process takes place in, or the line of interaction will remain same, or the motion of the bodies before and after collision will take place along the same line of action. Clear? This is known as line of interaction. Okay, line of interaction will remain same. So after collision, due to this normal impulsive force, the velocity of block 2 or M2 will increase, because initially it has velocity along this direction and the impulsive force also act along this direction. So it will supply an acceleration to this block M2. That's why it will move along this direction with certain final velocity V2, and this is known as the velocity of separation of the block M2. Similarly, the impulsive force N will oppose the velocity u1 which is along this direction initially. That's why the velocity of the block m1 will decrease when they get separated. So finally the block m1 will move along this direction with certain velocity v1. Clear? And here, due to this impulsive force, v2 becomes greater than in comparison to v1. This is the condition after collision. Clear? So as the collision is perfectly inelastic, so according to the condition we can write the total momentum of the system before collision will be equal to the total momentum of the system after collision. And also we can write the kinetic energy of the system before collision is equal to kinetic energy of the system after collision. We already studied in the case of perfectly elastic collision, these two are conserved. So this implies what is the momentum before collision of the system? It can be written as m1 u1 plus m2 u2, which is equal to the momentum after collision, that will be m1 v1 plus m2 v2. Clear? Similarly, for kinetic energy I can write first initial kinetic energy m1 u1 square plus half m2 u2 square must be equal to the final kinetic energy half m1 v1 square plus half m2 v2 square. Clear? So by rearranging this I can get m1 u1 minus m1 v1 will be equal to m2 v2 minus m2 u2. This can be written as m1 into u1 minus v1 equal to m2 into v2 minus u2. Let it be equation 1. Similarly, for kinetic energy by rearranging I will get half m1 u1 square minus half m1 v1 square is equal to half m2 v2 square minus half m2 u2 square. So by rearranging this we will get half m1 into u1 square minus v1 square, which is equal to half m2 into v2 square minus u2 square. Let it be equation 2. Clear? So these are two equations. Okay, m1 e1 minus v1 equal to m2 v2 minus u2, and half m1 e1 square minus v1 square equal to half m2 v2 square minus u2 square. Now dividing equation 2 by 1, what we will get? Dividing equation 2 by 1, we will get what? Half m1 e1 minus e1 square minus v1 square can be written as e1 plus v1 into u1 minus v1, a square minus b square equal to a plus b into a minus b, divided by m1 u1 minus v1 equal to similarly half m2 into v2 plus u2 into v2 minus u2 divided by m2 into v2 minus u2. So these two will get cancelled, m1 m1 will get cancelled, u1 minus v1 will get cancelled, similarly from m2 m2, and these two will get cancelled. So we will get what? And from these two sides half will get also cancelled. So we will get u1 plus v1 equal to v2 plus u2, or this implies I can write v1 equal to how much? v2 plus u2 minus u1. Let it be equation 3, or by rearranging this I can write u1 minus u2 is equal to v2 minus v1, where u1 minus u2 is what? Relative velocity of approach. v2 minus v1 is relative velocity of separation, and as here it is perfectly elastic, that's why these two are equal. Clear? So let it be equation 4. Okay, so now equation 3 gives us the value of v1 in terms of v2 and u2 minus u1. So what is the equation 1 we derive? Equation 1 is how written as how much? m1 into u1 minus v1 equal to m2 into v2 minus u2. Clear? So by replacing the value of v1 here, we will get what? m1 u1, in place of v1 I can write minus of v2 minus u2 plus u1, which is equal to m2 into v2 minus u2. Now simplifying this, we will get what? m1 u1 minus m1 v2 minus m1 u2 plus m1 u1 equal to m2 v2 minus m2 u2. Clear? So can solve this by rearranging it. m1 u1 and this is m1 u1, so it will become 2 m1 u1. So this implies 2 m1 u1 minus m1 v2, and taking this term along this side, it will be minus of, it will be m1 v2 and this is m2 v2, so this is m2 u2. Now taking m2 u2 to the left hand side, it will become how much? Minus m1 u1 plus m2 u2. So m2 minus m1 into u2 is equal to how much? Taking m1 v2 to the right hand side, it will become m2 plus m1 into v2. Clear? I am shuffling this, taking m2 u2 along this side and m1 v2 to this side. So this will become like this. So from this I can write v2 equal to how much? Just a minute. It will be m2 u2, this will be plus m2, this is your negative, so when it will take to the left hand side, it will become plus m2 u2 minus m1 u2, so it will become plus m2 minus m1 into u2. So we can write here v2 equal to m2 minus m1 into u2 plus 2 m1 u1 divided by m1 plus m2. So this is the expression for final velocity with which the block m2 will get separated. Clear? Similarly, if I am calculating the value for v2 from this relation, we can get the value of v1 in terms of v2. So similarly, from this equation, if I am writing v2 is equal to how much? v1 plus u1 minus u2, and proceeding as before, we will get what? The value of v1 equal to m1 minus m2 into u1 plus 2 m2 u2 divided by m1 plus m2. This is the final velocity with which the block m1 will move. So you have to remember these two final expressions. For v2, it is m2 minus m1 into u2 divided by 2 m1 u1 divided by m1 plus m2. And for v1, it is m1 minus m2 into u1 plus 2 m2 u2 divided by m1 plus m2. How to easily remember this? Just remember, here it is 2 v2, that means we have to subtract m1 from m2. This term is 2, that's why we have to subtract 1 from 2 into 2. Then m2 m1 e1 divided by total mass. Same as here, this is 1, so we have to subtract mass 2 from 1, so m1 minus m2 into e1 plus 2 m2 u2 divided by total mass. Clear? So these are the final expressions for the velocity of two bodies which are interacting one dimensionally during perfectly elastic collision. Clear? So there are some special cases. So you have to remember these two formula. So some cases, some special cases. So we have the formula for V1 equal to m1 minus m2 into u1 plus 2 m2 u2 divided by m1 plus m2, and for V2 we have the formula m2 minus m1 into u2 plus 2 m1 u1 divided by m1 plus m2. Clear? So these are the final expression for the final velocity of the two bodies. So the special case is when both the mass are equal. Okay, when both the mass are equal. So case 1, when m1 equal to m2. So what is the value of V1? If m1 equal to m2, here this term will become 0. So this will be 2m into u2 divided by 2m, because m1 equal to m2 equal to m. So in place of m2 I can write m, and this is m plus m 2m, so 2m will get cancelled. So V1 equal to u2. Similarly for V2, this term will become 0 because m1 m2 both are equal, so it will become 2m u1 by 2m. So V2 will become u1. That means when two bodies interact perfectly elastically in one dimensional collision and both have same mass, then their final velocity and initial velocity just get interchanged. The final velocity of the one will be same as that of initial velocity of the two, and the final velocity of two will be same as that of the initial velocity of one. Clear? This is the first case you have to remember, when both mass are same. Then case 2, when both mass are same, m1 equal to m2 equal to m. Okay, or first take both case 2 as u2 equal to 0. That means the body 2 is at rest. When u2 equal to 0, what is the value of V1? As u2 equal to 0, this term will become 0. So we have V1 equal to m1 minus m2 whole into u1 divided by m1 plus m2. Similarly, what is the value for V2? If u2 0, that means the second body is at 0 or rest. Then putting u2 0, this term will become 0, so it will become 2 m1 u1 divided by m1 plus m2. So when the second body is at rest, that means here is the condition when a ball strikes with a wall. Wall is the second body and it is at rest, so u2 is 0. Then what is the condition for velocity of u1 and u2 like this? Or when a body is at rest, not the condition of wall, just a ball is at rest and another ball collide with each other. Then these are the final velocity of the two bodies. Okay, when their mass are comparable with each other. Then if the second body is at rest, then the final velocity of both the bodies will be this much. Clear? Same case 2 but sub case 1, u2 equal to 0 and also provided m1 equal to m2 equal to m. Both the bodies have same mass and the second body is at rest. Then what is the value of V1? In this case, if I am putting m1 equal to m2, this will become 0, so V1 will be 0. So the first body comes to rest after collision. And what is the value of V2? So as m1 equal to m2, so it will become 2m, so v2 will be equal to vu1. That means when two bodies of same mass collide with each other, provided the second body is at rest, then after collision the first body which is moving come to rest and the second body gain the velocity or initial velocity of the first body and starts moving. Clear? The next case, u2 0, but m1 is very large in comparison to m2. That in this case the second body is at rest, but the mass of the first body is very large in comparison to mass of the second body. So what will happen? The value of v1, as mass m1 is very large in comparison to m2, so we can neglect m2, so it will become how much? m1 u1. As u2 is 0, this term becomes 0 divided by, as m1 is greater than m2, so here m2 is also get neglected, divided by m1, so we will get v1 equal to how much? u1. Similarly for v2, as m1 is very large in comparison to m2, so we can neglect m2 in comparison to m1, and u2 is 0, so this term will become 0, so, and this will become 2m1 u1 divided by m1, because m2 is negligible in comparison to m1, so v2 will become how much? 2 u1. Clear? Next case, same u2 is equal to 0, but m2 is very large in comparison to m1. That means the second body is at rest and the mass of the second body is very large in comparison to the mass of the first body. Then what will happen? What is the value of v1? As u2 0, then this term will become 0, and as m2 is very large in comparison to m1, so in this case I can neglect m1 in comparison to m2, so it will be minus m2 u1 divided by, neglecting m1 it will become m2, so m2 will get cancelled. We have v1 equal to how much? Minus of u1. That means the first body will start moving with the same velocity but in opposite direction. Clear? Then what is the case for v2? As u2 is also 0, so this term is become 0, but here the m2 is very large in comparison to m1, so we can neglect m1, so v2 will become how much? 2 m1 u1 divided by m2, but as m2 is very large in comparison to m1, so this ratio will be very neglect or it tends to 0, so v2 will be equal to how much? 0. Clear? So when a very large body of having very high mass is at rest and a very small body with certain velocity strikes it, like a ball strikes a wall, then if a ball strikes with certain velocity u1 with the wall, then the final velocity of the ball will be same u1 but in opposite direction, it will rebound back, and the same wall initially is at rest and finally the wall is also at rest. Clear? So these are certain special conditions during collision, and you have to remember the final velocity of separation for different types of conditions and the condition for the which we are calculating the final velocities. So this is all about your collision. Today we already discussed what is collision, the types of collision, what is coefficient of restitution and the different value of coefficient of restitution for different types of collision. Then we derived the velocity of separation for one-dimensional perfectly elastic collision, and you have to remember these two formula, and based upon these two formula we can derive the different special conditions and the different velocity of separation for different types of collisions. Clear? So in general, the velocity of separation for any type of collision can be given as a simple formula. You have to remember that formula, which you can apply to calculate the velocity of separation for any kind of collision. That is, I can write here the v1 can be written as, we already know what is v1, the velocity of separation of the body 1 can be written as p initial of the system plus coefficient of restitution into mass of the second body u2 minus u1 whole divided by m1 plus m2. Clear? Similarly, the velocity of separation of second particle can be written as initial momentum of the system plus E m1 u1 minus u2 divided by m1 plus m2. So these are the formula for velocity of separation for any type of collision. Okay, V1 and V2, where Pi is equal to initial momentum of the system along line of interaction okay. E is equal to coefficient of restitution okay. And another important point, V1, V2, U1, U2 all are taken along the line of interaction. Okay, if these are one dimensional collision, then you have to take complete V1, V2, U1, U2 because they are already along the line of interaction. But if they are oblique collision, then you have to take the component of V1, V2 and U1, U2 along the line of interaction. Clear? So these are two important expressions to find out the velocity of separation of two bodies after collision. Clear? So this is all about your collision. In next class we will discuss further. Okay, thank you.